All right, we're running out of space on this paper, so I'm going to copy this alcohol and this carboxylic acid and this other alcohol to a blank sheet of paper so we can talk through some of them. Whoops. All right, so you already identified that a carboxylic acid has a pKa of 4, that this alcohol has a pKa of 16. And then did you find a pKa, if you go to your quiz, do you find a pKa for an alcohol that looks like this? 10. That's different than 16. So rank these in order of acidity. This one's A, B, and C. Which is the strongest acid? A is more acidic than C, which is more acidic than B. Good, okay. Now let's explain why, because anybody can look up numbers and do greater than less than, but it's helpful to have some explanations as to why. And remember, when we're trying to explain about acids, we focus on the stability of the conjugate base. Acids are strong when they have very stable conjugate bases. CB is conjugate bases. So let's draw the conjugate bases for each of these acids. The carboxylic acid should be the carboxylate. The alcohol should be the alkoxide. And then C, that alcohol, this conjugate base, should also be an alkoxide with a negatively charged oxygen. So let's talk about differences of instability. Let's compare the carboxylate versus this alkoxide. Any reason you might expect, based on what I've told you, which of these conjugate bases should be more stable? Stronger acid has the more stable conjugate base, so the carboxylate is more stable. Now, we want to answer why. And when comparing stability, you want to focus in on the key differences. For example, start by asking, is the atom that holds the negative charge the same? In this case, it is. They're both oxygen, so that's not a difference. What other difference do you see? Go ahead.
In A and C, there's a double bond on the carbon that the oxygen is bonded to.
Ah, okay.
And then in A, it's a heteroatom instead of a carbon.
Okay. So you're noticing that the lone pairs that are associated with the negative charge are adjacent to a pi bond in both A and C, but you're noticing that the thing on the other side of that pi bond here is a heteroatom oxygen versus carbon there. And then what do you notice about the alkoxide? Have we got any pi bonds? No. Okay. What difference does that pi bond make? So think back, this was ancient history now. It was fairly early last week. We talked about something that can happen when lone pairs are adjacent to pi bonds. Go ahead. Resonance structures. Okay, so can I draw a resonance structure for the carboxylate? How do I do that? Very carefully. No. Take the lone pairs here and form a pi bond, and then to break the other pi bond and move it out onto the oxygen. So let's use the double-headed resonance arrow to draw the resonance structure of our carboxylate. We would conclude that the negative charge in the conjugate base of the carboxylate conjugate base is stabilized by resonance, and that importantly, the negative charge is shared between two oxygens. Is there any resonance stabilization for the alkoxide? There's no place for the arrows to go, right? You could do this all day till you were blue in the face, and that arrow isn't even meaningful, because if you push the arrow this way, there would be too many bonds to that carbon. You can't do resonance for a lone pair if there's not an adjacent pi bond, all right? So the alkoxide just has a localized negative charge. It is not resonance stabilized. Now, how about here? The OH bonded to that kind of a ring is called phenol, and the negatively charged conjugate base is called the phenolate anion. Can I draw a resonance structure for the phenolate anion? Yeah, okay, how do I do that? Okay, and then what? Put the lone pair out onto the adjacent carbon. We'll use our double-headed resonance arrows. Okay. Are there any other resonance structures I could draw? Turns out I could do it again, right? Can I do any more? Sure, one more like that. So for the phenolate ion, I have multiple resonance structures where that negative charge can be not only on the negatively charged oxygen, but also on these three atoms in the ring. Any questions about how I used resonance there? Go ahead.
I just wonder, like, why wouldn't the phenolate with more opportunity for resonance, I guess, or whatever, why would that not be more stable than the carboxylate?
Excellent question. Yeah, so you've noticed that the phenolate has more resonance structures, potentially more delocalization of the lone pair than the carboxylate does. So if resonance is the only thing going on here, you'd predict the phenolate would be more stable. But the pKa tells you that that's not the case. The pKa demands that you conclude that the phenolate is less stable than the carboxylate. So what else is going on here? What's the difference between those resonance structures? Go ahead.
Would it be that like carbon's less electronegative, so I can't find
Carbon is less electronegative than oxygen. What do you notice about the carboxylate? What atom holds the negative charge in this resonance structure? Still oxygen, right? In fact, in both resonance structures of the carboxylate, the negative charge is always on oxygen. How about the phenolate? It's on oxygen and on carbon. Carbon can't tolerate a negative charge as well as oxygen can. So that must mean that these other resonance structures that have carbon must not matter as much. Okay? So sometimes as you're comparing conjugate bases, you're looking for differences. You're like, okay, well, both of them are resonance stabilized. This one on the left, the carboxylate, must be better because in both of its resonance structures, the negative charge is on oxygen, and oxygen is more electronegative than carbon. Whereas for the phenolate, it is also resonance stabilized, but the other atoms that hold the negative charge are carbon rather than oxygen. So resonance is the reason why phenolate is more stable than the alkoxide, and electronegativity is the reason why the carboxylate is more stable than the phenolate. See the reasoning? Okay, let's do another, and this will answer a question that I think was on your quiz that we didn't quite get to in item 1. Here is a ketone. Some of you looked at that and thought, what on earth am I supposed to do? There's no bonds between hydrogen and a heteroatom. And the answer is, okay, well, if I need to draw its conjugate base, then I gotta start looking for other types of bonds with hydrogen. So you can sometimes think about CH bonds as being acidic. What would I get if a base attacked the sigma star of this carbon-hydrogen bond? Where would the negative charge go? Have to go onto the carbon, right? So the conjugate base of that ketone is this molecule, which happens to be called an enolate. If I did the same thing over here, the conjugate base would be this negatively charged molecule. Now it turns out the pKa's of the two protons are dramatically different. The pKa of the proton on the left is 20. Now that's way less acidic than an alcohol, but as you'll see, it's incredibly more acidic than the hydrocarbon. In other words, your regular normal sp3 carbon-hydrogen bond is not very acidic. However, when you've got an adjacent carbonyl, the proton gets more acidic by a factor of 10 to the 30. That's a massive improvement in acidity. Just for talking about molecules, if I want to say I'm adjacent to a carbonyl, the carbon that is adjacent to the carbonyl, I'm going to call the alpha carbon. Alpha is for A, alpha is the Greek letter for A is for adjacent. Okay? So protons that are alpha to carbonyls are more acidic than regular CH bonds. Let's talk about why. What has the conjugate base here got going on for it that the conjugate base here doesn't? Same thing, right? You got the adjacent carbon-oxygen pi bond. I can move the electrons here and then move those there. I get this alternative resonance structure where I can now have a negative charge on a more electronegative element, oxygen, rather than carbon. Of course, resonance tells me that the negative charge is in both locations. But yeah, the enolate is resonance stabilized and therefore way more stable than this localized anion. And this is important. You will see in biochemistry that we will sometimes remove protons that are alpha to carbonyls. And the reason we will do that is because their conjugate bases are stabilized by resonance. That kind of thing becomes important in a lot of reactions in biology. Okay. Questions about drawing conjugate bases? Questions about comparing acidity? Yeah.
Do we have to draw the lone pairs when we're drawing them, or just we have to show how they
Yeah, if you draw a conjugate base, you don't have to draw the lone pair as long as your formal charge is correct. Yep. Okay, others? Yeah.
Can you explain that?
Oh, earlier, I can do that just here. Earlier we were comparing, I think, these two acids, pKa 11 going to the neutral amine versus the imidazolium ion in which we went to the neutral imidazole. And we were focusing on the stability of these two conjugate bases. And the pKa tells us that the imidazolium ion is more acidic. Therefore, the pKa information demands that we conclude that the neutral imidazole is the more stable conjugate base. The question is why? So you start looking for differences. Are they on the same kind of atom? If one of them was oxygen, one of them was nitrogen, that'd be easy because oxygen's more electronegative than nitrogen. Here they're both nitrogen, so there's no difference. Resonance stabilization of the lone pair? No, not really. For reasons that we can talk about later, but mostly because the lone pair there is in an sp2 orbital. And for that, we'll have to wait a little while before it makes sense why the nitrogen there is not really stabilized, why the lone pair there is not really stabilized by resonance. For now, let's just talk about if the lone pairs are held on the same kind of atom and resonance isn't an issue, then you want to start looking at the hybridization of the atom with the lone pair in the conjugate base. So this nitrogen is surrounded by 4 groups. The nitrogen is sp3 hybridized. Does that make sense? So you would conclude that that lone pair must be in an sp3 orbital. Does that follow a little bit? Yeah, an sp3 hybridized atom makes all of its bonds with sp3 orbitals, and if there's any lone pairs left over, those are also in an sp3 orbital. This nitrogen is surrounded by only 3 groups, a lone pair and 2 carbons. So that nitrogen has to be trigonal planar and sp2 hybridized. sp2 hybridization means I have 3 sp2 orbitals and 1 p orbital. We can check off this sigma bond is an sp3 orbital, involves an sp3 orbital on nitrogen. This one does too. The pi bond involves a p orbital, so the only thing that's left for the lone pair to be is in an sp2 orbital. So how do you expect lone pairs to differ in stability based on whether they're sp3 versus sp2? An sp3 orbital is 25% s and 75% p. That's what the superscript p3 means. 3 parts p, 1 part s. And then the sp3 orbital is 33% s and 67% p. The sp2 orbital has more s character, what we will call s character. That means there's just more of an s orbital in an sp2. And s's are lower than p's, so the more s orbital you have, the lower in energy it is. So being in an sp2 orbital is more favorable, lower in energy than being in an sp3 orbital. Okay. All right, we need to return to something I said a while ago, and that was that if you understand the definition of Ka and pKa, that you can determine, based on the pH of the solution that you're in, what should be the major form of a molecule that has an acidic proton in it. Okay? So let's do this for a carboxylic acid. Let's assume that you put a small amount of a carboxylic acid in a solution of water, and the solution of water is buffered at pH 7.4. You may have learned about what a buffer is in general chemistry. A buffer is something that keeps the pH constant. We're not going to worry too much about how they work. Your blood does this for itself. If it didn't, you would die. And if you've ever hyperventilated and started to get dizzy, one of the reasons is if you exhale too much CO2, your blood starts to get too acidic. You throw off the buffer balance in your blood. It's called too basic respiratory alkalosis. Anyway, one of the two, I forget. In any case, let's assume we put a small amount of this carboxylic acid in a solution where the pH is constant. And we ask ourselves, what should the major form of that carboxylic acid be? Should it exist in its neutral protonated form or in its negatively charged conjugate base form? So to do this, let's identify the acidic proton in the carboxylic acid. And its pKa, as we've learned today, is 4. Okay. 4 minus 7, is that a negative number or a positive number? That's all we need to know. It's a negative number. Okay. Now, if this side of the equation is negative, What does that tell me about this ratio here? Is it greater than 1? Is it equal to 1? Or is it less than 1? Okay, we need just a brief review of logarithms, okay? Logarithm of 10 equals 1. Logarithm of 1 equals 0. And logarithm of 0.1 equals -1. And I should probably rearrange things like this. If the difference between pKa and pH is positive, the ratio here is going to be greater than 1. If the difference between pH and pKa is 0, the ratio here is going to equal 1. If the difference between pKa and pH is negative, the ratio here is going to be less than 1, a fraction. Okay? So, let's ask that again. 4 minus 7 is a negative number. That means this ratio inside the log should be what? Should it be greater than 1, equal to 1, or less than 1? Less than 1. It should be a fraction. Now, here's the jump. If this ratio here is less than 1, is a fraction, which one is bigger? The concentration of the acid or the concentration of the conjugate base? Conjugate base, right? So, you can conclude at pH in your blood 7.4, the carboxylic acid loses its proton and exists as the carboxylate. And some people don't like equations. I don't know who you are. If you hate equations, I can't identify with you because I love the maths and I love the equations. But that's okay. We all like different things, and I'm a nerd already. If you don't believe that I'm a nerd, you should walk by my office and see all the Star Wars Legos. My office is a nerd haven, and I'm so grateful that I have a job and an office, because Amber would not be really that okay with all of the Legos I have hanging around our house. To say nothing of the fact that the children would have destroyed them, but there I can keep them safe and nice without having to use super glue, right? If you don't like math, think of it this way. If pKa is greater than pH, the HA form dominates. The acid keeps its proton. If pKa is less than pH, A minus dominates, the conjugate base form dominates, and the acid loses its proton. I've taught this for a number of years, and students always struggle with this. Some like to see the equation, some like to memorize the words and the rules, and I'll say it 2 or 3 times, and they'll say, okay, wait, if pH is, and so we have to go back, you're gonna have to work on this and practice it to get it. If pKa is greater than pH, the proton still is on the acid. If pKa is less than pH, the acid loses its proton. Okay? So let's do this for some of the acids that we just looked at in the quiz. We just did the carboxylate. So, and question 3 says we're going to circle the form that would exist in your blood at pH 7.4. So for the carboxylic acid, which is it? 4 is less than 7, point whatever. So if pKa is less than pH, the acid loses its proton. So the carboxylate form should dominate. Okay? How about the alcohol? Go ahead, sorry. That was here. I said we're going to pretend that pH is in your blood. Some of these molecules you would not want in your blood, but we're going to pretend like they are. All right, the alcohol. pKa 16. At pH 7, which form dominates? Acid or conjugate base? Acid. If pKa is greater than pH, and we're saying that in blue, pH equals 7.4, the acid form should dominate. Okay? How about the thiol? pKa 8. Yeah, the acid form should dominate, but going back to that equation, the difference between 8 and 7 is only 1. Right? And so that means the acid form dominates, but only by a factor of 10. That means that at physiological pH, you might expect there to be some amount, and in fact it's less than 1, isn't it? 8 minus 7.4 is 0.6, so we could figure out what that ratio was. In any case, you would expect there to be, at physiological pH, more of the neutral acid than the negatively charged conjugate base, but you'd expect some of the negatively charged conjugate base to be there too, okay? And you would not be worried if you were doing chemistry and it required you at pH 7 to remove that proton, because you know that that would be a pretty reasonable step in pH 7 water. How about the phosphoric acid? Here there are multiple possible equilibria. The phosphoric acid loses its first proton with a pKa of 2. Second was 7.2. I didn't tell you this, and it's not that relevant for our discussion, but going from the dianion to the trianion has a pKa of 12. So we can do this one by one. At pH 7, which form dominates, acid or this conjugate base? Conjugate base. So we're going to rule out the acidic form. Now, how about this second equilibrium? At pH 7.4, which one should dominate? It's going to be pretty close, right? Remember, if pKa and pH are equal, you got about a 50-50 split. So they're not quite equal. 7.2 is a little bit different from 7.4. So if anything, at 7.4, there's more of the dianion than there is of the monoanion. But I would expect there to be something like close to 50-50. So you're going to see that when we draw phosphate groups like this in biology, it's going to be totally fine to draw them as the monoanion or the dianion. Both are reasonable at physiological pH. Same thing for the phosphoester. We would conclude at pH 7, you're going to have a mixture of those two. Yes? No, the 7.2 only refers to the monoanion. So you could look at the dianion and say at pH 7, is this going to lose its proton with a pKa of 12? And you conclude no. If pH is less than pKa, the proton is still there. So what we conclude, there are 3 different protons to be removed in phosphoric acid. We conclude that the orange one is gone and the pink one is gone, but the green one is not. Yeah?
So, for this problem, would we draw the conjugate base of the first one, or would we draw all of them?
So I only asked you to draw the conjugate base of the first one here, but I added more information as we were going along. Yeah. Okay, good. How about the ammonium ion, pKa 11? What do you expect there? Acid form, yeah. You will see that amines are always positively charged at physiological pH. Under some conditions, they get deprotonated to do reactions, but for the most part, at pH 7, the amine's going to be positively charged. Same thing with the guanidinium. How about the imidazolium ion at pH 7.4? Is that proton still on or is it off? Off. 7's greater than 6. If pKa is less than pH, the proton is off. So we expect the neutral form to dominate. Nevertheless, it's not dominating by that much. 7.4 minus 6 is only about a factor of 10 in log units. So you would expect there to be mostly the neutral form, but some of the positively charged form present as well. Okay. So this now allows you to do my favorite problem that I give to people when I teach 351 and 352. I give it to them during the first semester and they get it wrong. I give it to them again in the second semester on the first exam and they get it wrong. I give it to them again on the final and they get it wrong. You are all going to get it right and be better at this than them, okay? And this is the problem. Behold the scary molecule. If any of you like to or already know amino acid structures, this peptide or this structure of amino acids linked together has the sequence VENTRESS. That's Ventress. She's a character in Tales of the Underworld, which just dropped yesterday on Disney Plus. It's a Star Wars cartoon. So anybody that cares about the lore, that's where that peptide comes from. In any case, what we want to do is we want to identify all of the acidic protons using the pKa table on the back of your quiz. I'm going to give you a brief hint. Amides are not amines. Okay? So you might look at something like this and say, oh, if that were positively charged, it would have a pKa of 11. That's not true. The presence of the carbonyl adjacent to the amide nitrogen changes its acid-base properties. So for our purposes, we're going to ignore the amides. The other clue is this. Shown here, some neutral groups have negatively charged conjugate bases, and some neutral groups have positively charged conjugate acids. Let's give you some examples of both. Where do you see a neutral group that would have a negatively charged conjugate base? Yeah, carboxylic acid. Good. And what is the pKa there? You could look it up again. I'll just tell you. It's 4. Okay? So now you can make the judgment at pH 7, what form should that equal? Negatively charged conjugate base, which I'm going to draw. So at pH 7, that carboxylic acid should be negative. Same thing for that one, right? Same kind of carboxylic acid at pH 7, which is greater than the pKa, the proton gets removed. What about here? This is an amino group. It's neutral. We talked about amino groups versus ammonium groups. This molecule is drawn neutral to sort of trick you, but you need to consider the positively charged conjugate acid. So let's draw the conjugate acid of the amine group. What is the conjugate acid of that amine? NH3, plus. And if you look up its pKa, you expect it to be around 11. Okay? At physiological pH, which form should dominate? Positively charged acid or neutral base? So pH 7, going back to our equation, if pKa 11 is greater than 7, the conjugate acid form dominates. This was the thing that people really struggled with when I taught this previously. They have a hard time looking at a neutral group like the amine and then remembering its positively charged conjugate acid. Okay, there's 2 more groups there that are either 2 more groups there that have pKa's that we should worry about. Where's one of them? I see a carboxylic acid there. and that pKa is 4. So again, you expect negatively charged. And you may recognize this as an example of the guanidine functional group that we learned about earlier. It has, if you were to look at your table, a positively charged conjugate acid, the guanidinium group. I should put the arrow this way. The pKa there is 12. At pH 7, which form should dominate? The positively charged guanidinium acid or its neutral conjugate base? Acid, because pKa is greater than pH. Okay. I'm not worrying about this group because that's an amide, and amides are not amines. We're not worrying about proton transfer groups with amides. Another thing I haven't done is worry about these OH groups. Why didn't I worry about those OH groups? What is the pKa of an alcohol? 16. At pH 7, should the alcohol still have its proton? Yep. When pKa is greater than pH, the proton is still on there. So alcohols are neutral at physiological pH. Now this question requires you to go through each of those groups one by one and get the conjugate bases or acids right, draw their structures right, and get the charge right, and then add it all up right. So there's a lot of ways you can get this kind of question wrong. What's the overall charge? I see a plus there, and then 3 minuses. So yeah, overall charge -1. And you're going to see this in a multiple choice format. I'll give you a scary molecule like that. Maybe it will say Darth Vader is coming for you or something like that. And then it'll be options A through J, -1, -2, -3, -4, +1, +2, +3, +4. Yeah.
Could you just say the amine one more time? Sorry.
Amides are not amines. Amines are bases. They can pick up protons to have a positively charged ammonium form. Amides are not basic because the lone pair is stabilized by resonance with the adjacent carbonyl. So I am ignoring, I'll highlight in gray, all the amides in this molecule. I'm ignoring all of them. There is a problem like this, but worse, on your problem set. I encourage you to get started on it now, and then I can answer some questions next time. Go ahead.
Should we memorize conjugate bases and what would be a chart?
Should you memorize pKa's? No, there'll be a chart. You need to know -2 for hydronium and 16 for alcohols. Otherwise, there'll be a chart. Yes?
So for all the colored amides
The things that are highlighted are in gray are not acids. The yellow stuff and these are acidic groups. And I guess, yeah. All right. Thanks, everybody. I'll see you tomorrow.